Good afternoon, everyone. Any questions? But I have a question. Did anyone look at my solutions to homework 2?
Yeah.
So if you haven't looked at them, have a look at them. A, so that you can marvel at their conciseness, and B, that you can see how I set up the unit tests, because I used the same scheme that you should be using for homework 3 to use the Scala test thing. And so if you look at mine, I think you'll find the Scala test is no big deal. It's just like JUnit. And also you see that SBT structure with all those directories. Now, so there was someone on Piazza who said, that's crazy to have all of these directories. And I do agree that it seems quite overblown. But then the tools make them for us, and there's no sense in fighting the tools. So whether you like it or not, just live with that directory structure. The other thing is, and when you check in, so when you make a project with this SBT thing, it produces a huge amount of extra files, and make sure to set up your git ignore so that it doesn't check them all into the repo. It just looks unprofessional otherwise.
Well, your instructions said to actually go to your temp directory when you do the commands.
No, that's just Okay, let me be clear about that. The thing with the temp directory, that is after you have things checked in. So what I always recommend is that after you have everything checked in, you pushed everything, that afterwards you go to the temp directory, make a clean checkout of your repo,
Right. Yeah.
so that you can see what the grader sees. Because it is a distressingly common thing that people forget the final push, or they forget to add something, right? It's very easy to forget a git add. And then when you see that the files that you thought were on the repo just aren't there, then it's an easy thing to fix it. So it only takes a couple of minutes, and it really can save you from embarrassment. Also in the exam, I highly recommend that you spend the extra couple of minutes to do that, because if you don't push it, or if you don't push it but it's already committed, it's one thing. But if it's not even committed, there's no proof that you did it during the exam, right? So it really is a good idea to have that other check. I mean, you can always, of course, just look at the website and see if things are there. But I find it easier to just clone it and run a quick test. All right. So yes, make sure to look at the solutions that I gave out. It shouldn't take you very long. So today we're going to be talking about higher order functions. So, and the definition of a higher order function is something quite simple. It's a function that consumes a function or that produces a function. So a regular non-higher order function would just consume or produce integers or strings or lists. But a higher order function eats a function, or it spits out a function. So here's an example of a higher order function, map. We've seen map several times now already, and it's a higher order function because it eats another function, the function that it uses to apply to each of the elements. And you've seen other higher order functions, such as filter or reduce. That filter takes a predicate, reduce takes an operator, and those are all higher order functions. So it doesn't look like a higher order function is anything particularly difficult. It gets a little bit more intricate when you have the other kind of higher order functions, the ones that produce new functions. And so you might say, why would you ever want to produce a function? And I'll give you plenty of examples. And the other is, well, how are you going to produce a function? So let's go through both of those. So let me give you a motivation of why you might want to produce functions. So we've seen these functions, triple and quadruple before. Triple multiplies by 3, quadruple multiplies by 4. And then you can use those functions by passing them on to a map. Well, at some point you say, well, I don't want to have to write a separate function for each factor. So you write a function that multiplies by a generic factor. So we call it multiply by. And so here's multiply by. You feed it the factor that you want, and it produces a function. So multiply by of 5 is a function. Multiply produces a function giving an integer. So this is obviously a useful function that can produce other functions. And what you do with those functions that it produces, you can pass them on to map, for example. So here you have a very simple example of where you might want to produce a function. So now we need to figure out how to do this. And there's a general recipe that you follow. And it's quite simple. So you ask yourself, what does multiply by of 5 need to produce? It produces a function. What kind of function? A function that takes an integer and returns an integer. So it produces a function whose type is int to int. That's what it produces, right? So you can say multiply by consumes an integer and produces an integer function. So it's really helpful if you can look at something like int to int and identify with it as one thing. It's an integer function. So here I'm writing the return type. You see there's a colon and then int to int is a type. I'm writing the return type even though it's not strictly required. In Scala, you can omit the return type except for recursive functions. This multiply by function is not recursive, so I could omit it, but it's actually a pretty good sanity check. And so I've seen quite a few Scala programmers who swear by always declaring the return type. That way, if you mess up, that if then the inferred type is different than the one that you declare, you get a very clear error message. Otherwise, you'll eventually get an error message too, but it's not at the same spot where you might be looking for the fix. All right. So how far have we gone? We said multiply by. We said what it consumes an integer. We said what it produces. Now we need to deliver on that promise. We need to make an int to int. How do you make an int to int? Well, you have to write x colon int and then an arrow. That's how you always write an int to int. So, and this thing now produces something. What do you put for the dots? Well, that's where now you actually have to think about what work you want to accomplish. Everything until this spot was just pure formalism. Well, we just said, what does this thing eat? What does it produce? And then what is the syntax required to get there? They had nothing to do with any thought at all. It was just really throwing the syntax together. Now, finally, we want an answer, and the result, of course, is n times x. Because when you have an x, then you want to multiply that by it. And so this is the general structure that that you want to use. You always ask yourself what goes in, what comes out, and when what comes out is a function, then you write the skeleton of what you need to produce that function, and then you finally worry about what that function needs to deliver. So when you put it all together, then it looks like this. And a lot of people, when they look at this, they say, this is really kind of not so easy to read. There's a lot of arrows and stuff, and that is undeniably true. I always find it much easier to write these things than to read them later. Because when you write them, you just follow the forces of logic. You very rarely have any choice at all, and then it's pretty easy. But when you look at it, then you kind of scratch your head and say, okay, you really have to think this through, because you have this function producing a function. Now, here I've now omitted the int to int again, and so I leave it to you to see which of these two forms you prefer. It does seem to be a personal choice. So I tend to omit them, but like I said, many people do leave them in. But at this point now you have to look very careful, right? You see that it is the parameter type is an integer, of course, and then what does it produce? So it produces this function. So that gets us to the syntax. I want to get into a situation. Yes?
For the inferred return type, what if you use like a string or an integer? Like how would it do?
So if over here I were to say colon string to integer, it would just tell you that that's not, there's a mismatch somewhere.
Okay.
Try it out. Just copy and paste this thing and change this to string, that to string, and you'll see what it does. So the Scala error messages are not always the friendliest, but it is usually worth your while to try to figure them out. Yeah, particularly when you come from Java, where if they had 20 years to try to make the error messages better, and they're really, there's an effort every time to clarify obscure error messages. In Scala, it's not quite so much. So oftentimes the messages can be a little wrong. So I want to motivate the use of these function-producing functions with a somewhat realistic example. So first of all, if we want to sort something in Scala, we say sort with, and you give it a comparison function. The comparison functions in Scala work a little different than in Java. In Java, you may recall, you have these things like comparable and comparator, and then the compare to, or the compare function returns 0 if the parameters are identical or undistinguishable, a positive value if the first one should come after the second one, and a negative value if the first one should come before the second one. And that's a perfectly reasonable thing to do. In Scala, it works a little bit different. The comparative functions don't return an int, they return a Boolean. They return true if the first parameter should come before the other one, and they return false in all other cases. That's maybe a little bit more logical, right? But because you just use the relations from mathematics instead of this funny +1, -1, or 0. But it's not quite as efficient in all situations, as you will see later in the lab. Anyway, that Scala does what it does. And so you give it a function that compares two things and gives a Boolean to see whether they're in order or not. Here I want to sort this thing by decreasing size. I want to have the largest ones to the front. And so then I say, if the first one is larger than the second, then that means they're already in order. And that's a comparison function. Now, what I want to do in the next couple of slides is I want to produce other comparison functions. And a common way of comparing things that are not integers, a common way of comparing things is to take the thing and map it to something that is an integer, and then compare the results. So for example, say I want to compare strings by length. I have a list of strings. For each of the strings, I compare them by length. I compute the length, and then I compare the resulting integers. And so that's what my comparing by thing is going to do. Comparing by is going to take like a measurement function, or as they call it, a discriminator function, and it's going to turn that into a comparison. And they're slightly different things. A measurement function just takes a string and measures it. That could compute the length, or it could compute whatever. Maybe there's a number in there, and it converts that number to something. So that's my discriminator function. And a comparator is something that takes two strings. So I need to bridge the gap between the two. So comparing by produces a comparison function. That's a function, string to Boolean. Again, think of this thing here as a thing. It's a comparison function. So I'm producing a comparison function. I'm eating a measurement function or a discriminator function that turns strings into integers. So let's start writing it. It starts out easy with def. It's still pretty easy. We have to give the thing a name. It's comparing by. Now I need to see what are my inputs. The input is a function, string to integer. So I write string to integer and I give it a name. I can't think of a good name, so I call it f. And then it produces something. What does it produce? I already wrote that down. It produces a string to Boolean. What's a string to Boolean? It is something that takes two strings and returns a Boolean. So I write x colon string, y colon string. I can't think of any better names, so I just do x and y. I can always rename them later. And now I need to produce a Boolean. Now I've done as much as I can from just the logical requirements, and now I have to do a little bit of work, but it's simple. So I have these two strings, and I want to say, when does x come before y? And it is if the measurement of x comes before the measurement of y. So that's my function. If you put all of this together, that's my higher order function. It is a function, so comparing by is a function that eats a function and produces a different function, slightly different function. In the Java library, there is a thing like that. Trying to remember what it's called. It's called comparator.comparing. It works the same way. So if you use Java 8 or Java 9, it's a common way of these days of using comparators. So I'm going to make this comparing by function generic, and that's something that we haven't covered yet, and we won't cover for several more weeks. So I'm just going to show you how to do it, and you should just take the syntax on faith. So I want comparing by to work for any type T. So I want to be able to compare things, whether they're person objects or string objects or whatever. And I want the result of the discriminator to be not just int, but anything that can be compared. And in Java, you would say anything that implements comparable. Here at Scala, it's a little different. We say that the result type R needs to conform to the ordering type bound. And we're not going to get into that maybe at all in this course, because that's the way that works is a little advanced. And then I also have to do some mumbo jumbo to make the ordering thing work out. And don't worry about this import line at all. There's some real magic going on here. But then the code itself is the same. I have an x and y that are both of the type that I want to compare. And I measure them by using f, and then I just compare the result. All right. So once I have this done, now I have a truly useful thing, because if I have any old collection of objects, I want to compare by some characteristic of those objects, then I don't have to do much work at all. Here, for example, I have a class person. A person has a first and a last name. This class is called a case class. That's something that we're going to be covering in a week or two. But I can tell you very simply what a case class does. A case class gives you for free the constructor, so I can just construct a person like that, and the accessors to the fields. So right now I can say, if this thing here is an object, I can say o.first. Or here, for the in general, I can say _.first. That's the function that gets me the first element. And the word case here means that I get these accessors and those constructors for free. That's really all it does. So yeah, I'm making a list of people. And if I want to sort them by their first name, then I use the discriminator function _.first. That thing takes a person and returns the first name. I call comparing by, the generic one here. That will make it so that the discriminator function is called on each of the people, yielding a string, and then the sorting happens by the strings that result. So that's obviously a useful thing to do. Now, actually, I want to do something even better. I want to be able to do it so that if two people have the same first name, then I want to use the last name as a tiebreaker. Well, that's the job for yet another function. I will call that function breaking ties. Breaking ties consumes two comparators. They can be any comparators. They don't have to come from comparing by, but in this case they do. It takes two comparators. It tries to use the first one, and if the first one can tell the two apart, then that's the answer. If the first one doesn't distinguish between them, then the second one is used to break ties. So breaking ties is a function that consumes two comparators, and it produces a comparator. Yes?
How does it know if they're equal if you only know true or false?
If it makes the comparison x less than y, and the comparison y is less than x.
Oh, okay.
If one of them gives you a true, then you have the answer. If both of them are false, then they're indistinguishable.
Yeah.
Yes?
And this breaking ties looks at in priority of whatever's the first
Yes.
parameter? And
Yes.
the
So
second.
breaking ties will say this one is the more important one, and that's the less important one. Clearly one could generalize breaking ties to take like an arbitrary number of parameters, but we're just going to do this two right now.
Yeah.
Yes?
I'm still kind of confused about that point. So it would return a Boolean, and if it
No. Okay, before I say no, what returns, what's it?
so the actual comparing by, it would return a Boolean if it's only greater than the previous.
This comparing by does not return a Boolean. What does comparing by return? Yeah, a comparator function. So if you look at the code for comparing by, you can see what it returns. It returns this function here. That's why I'm asking at which level do you mean the Boolean?
So if the two functions within comparing by were both the same, they return the same value. how would they distinguish between those two?
Well, at that time, the function would say, I'm not telling you to put one before the other.
Okay.
So let's say that you have two strings with the same length. Then the function would not say that the first one is less than the other. It would have no opinion on that. It would simply say, well, I'm not telling you to put one before the other.
Okay.
And in some algorithms, that's all the information that you need for sorting. Actually, that's good enough. You don't. But sometimes, in some situations, you really do want to know whether they are indistinguishable or not. In that case, you have to call them in both directions. And that's a little wasteful because with the Java approach, you have the answer with a single call. But if in this case, you sometimes have to call twice. So, let's move on to write breaking ties. What does breaking ties produce? It produces a comparator. That is a function that eats two person objects and produces a Boolean. Here I'm writing it for person objects only. Clearly I could eventually generalize it to any type T, but I think it's simpler to understand if you use a specific type first. So, breaking ties produces a person to Boolean comparator. That's a person, person to Boolean. What does breaking ties consume? It consumes two of those comparators. So it consumes two things that are each a person to Boolean. Yes?
It sounds like the composite pattern. Is that like, is there a name for it?
It certainly, you could think of it as being a composite, right? Because a composite means that so in an object-oriented view, where you would say, this thing is a class that's imbued with these characteristics, you would say this thing has two comparators, and it also is a comparator. From a functional point of view, I'm not sure that's really how I would look at it. I would maybe call it an operator. An operator is something that takes two things and produces something off the same thing again. So, breaking ties, I write def, I write the name, I write the first parameter type, the second parameter type, I give them each of these variables some name. I can't think of anything better. I call it C1 and C2. Maybe I should call them first and second or something. But here you go. And then I write an equal because now I'm done with the parameter types. Now what is the return type? The return type is the first person to Boolean. So I have to produce one of these things. How do I produce it? Well, to produce a person to Boolean, I have to take the person, stick parameters x and y in here, and then put an arrow and put an answer in here that's Boolean. That's the part that writes itself. There's no particular logic in there. As long as you have written down on a sheet of paper what it is that the parameter types are and what the return type is, then this here is completely mechanical. I do think it's a good idea, particularly in the beginning, to write that down separately so that in your mind it's very clear what does this thing eat and what does it produce. And the reason it's important is that, as we were just having this conversation where I was confused about your question, is that these things work on so many different levels, right? We have the Boolean. Well, what's the Boolean mean? I mean, there's three Booleans here that are floating around, and so it's really a good idea to do this slowly and mechanically. All right, so now we do need to produce this Boolean answer here. So what do? We compare two people with the first comparator. And if the first comparator says x comes before y, then we have our answer. Now we see it. Compare x and y with the first comparator. If it says true, that means x comes before y, then we say in the composite one, we do agree that x comes before y. Otherwise, we compare them the other way around. So now C1 tells us that y comes before x. In this case, we're absolutely sure that x does not come before y. And we're reporting that we have an answer. And in the other case, we're not really sure. X and y are undistinguishable. In that case, we use C2 to tell the difference. C2 could also say they're undistinguishable, but that's not our problem. So that's the code. So when you put it all together, you have kind of depending on how many lines you want to write, but a very compact way of doing this comparison. So this is, I think, a good example of a function that has some real-world use, that glues together two comparators into another one, and you just really need this notation. Can you do this in Java? You could do the same thing in Java, but in Java you would each two comparators and produce another comparator, and the amount of technical mumbo jumbo that you have to make a whole new class. You have to make an object of that class. You have to define the function of that class. It's a lot more work. So a little bit more syntax that's useful in this context. It's called currying. Currying is very simple. It means you'd have a function that takes two parameters, and you turn it into a function that takes that has only one parameter and produces a function that has the other parameter. No one understands that when they first hear it. So I certainly didn't. So let's look at an example here. So I'm using a boring function, multiply, has two parameters. And now I'm going to write this a little bit differently. I'm going to, instead of having a comma here, where it has two parameters, I'm going to put in a parenthesis here and another parenthesis here. And so this is what's called the curried form of multiply. Currying means instead of having more than one parameter, you chop it down to one parameter and then you pass the other one like that. Now when I call it, it still works the same way. So multiply of 3, 4 is 12, and when I call it, should be multiply. Multiply of 3, 4 is still 12 because 3 goes in here, 4 goes in here, and the result is 12. Yes?
If you were to write to the return type, would it still just be assuming the two parameters?
So the return type of this thing is it. But you're asking, what is the type of this thing?
Yeah.
I'll tell you what the type is right now, and I'll explain it in a minute. So the type is int to int. And I'll actually, the arrow is right associative as it one sets the parentheses like this. So let's see, and this is exactly what the next slide tries to, the next bullet tries to get at. Multiply of 3, what is multiply of 3? Well, you can see from here what multiply of 3 is. It is something that is capable of eating 4. And then it produces 12. So multiply of 3 is clearly a function. It's a function that can eat an integer and produces another integer. And so which function is it? Well, clearly it's this function, right, that multiplies by 3. So multiply of 3 is the same thing that we previously called multiply by. And so that's really what the syntax here would say, that multiply, the curried form of multiply, consumes an integer, and then it produces an integer function. The one that does the multiplication by the first thing. Now, it's all kind of abstract. And so you may wonder, why would you want to do this? And there is a theoretical reason that you can actually say that in a type system, you never have to really worry about functions with more than one argument. That there are just special cases of functions with one argument, because you can always use this currying trick. But the other one is, it also makes it a little bit simpler to write higher order functions. So if we look at the comparing by function that I had written before, when I write it in you've seen it before, I said comparing by consumes this thing, and then it produces a function. But I can write it in a curried form, and it's exactly the same thing, by then putting the parameters of the function that it produces in here, and then have an equal, and then have this expression here. Some people like the curried form much more and find it easier to read. But it does, of course, hide a little bit of what's going on, right? That comparing by really produces a function. So you want to ultimately be able to go back and forth between these two representations. So this thing means exactly the same thing as we've had in the slide before. It's just a different way of writing it. And I guess, and I should maybe rewrite the slide to make it even clearer. Remember how previously we said that when you say def f, that's the same thing as saying val f equals, and you rewrite it with the arrow. And it's the same thing when you have more than one argument. So you can say that moving this thing over here and replacing the arrow with the equal sign is really what's been happening here. In the old form we had the parameters and the arrow here, and now I've just moved them to the left. So that syntactical trick is called currying, after the fellow here on the left, the logician Haskell Curry. All right, that's enough theory for now. So let's do this lab. And it's a short lab. It only has 3 steps, and I thought it was the most trivial thing in the world, and it took the people in the first section a long time. So try to get past step 1 as soon as you can. If you have any questions, and people did have an amazing number of questions in the other section, let me know. I'll try to help out. So I'm just going to start from scratch here. So here we're having our list, and the first thing we wanted to have all of the short strings in the list. So that's of course filter. So I watched a number of people who were struggling with this, and they were trying to use map or something. But map isn't going to work, right? If you apply map, then you get a list of lengths, but it doesn't really help you. So you do have to make an effort to memorize what's map, what's filter, what's reduce, what are these basic kinds of functions. They will occur all over again, and so it's not a waste of your time. So in this case, I can just call dot length less than 5. So come on, stupid worksheet. Here we go. And then I get the short strings, right? So the insight here is that this is a perfect situation for using the underscore. There's no need to come up with any long variables. Now, what was the next thing? The words sorted by increasing length. So that's sort with. So here's a concise answer, right? Each underscore is a separate variable, and yeah.
Can you use sort by?
I'd have to look at what the heck does sort by do.
Just erase everything after the first underscore dot length and replace sort with sort by. So it'll sort by.
Oh, you can do that too. Yes. So sort by uses the discriminator function. Yes. So you could have, if you know about sort by, you can do that. But that's not what I expected people to do.
Oh, well.
But if you want to use sort by, go for it. Yeah.
Is it sorted?
Yeah.
Are they the same? Or
Sort with uses a comparator. Sort by, which I've kept that from you because that would have ruined my motivation for the first part of the lecture. Sort by just uses the discriminator function.
You know what? Yeah, you're right. It automatically does that like greater one.
Yes. So.
Oh yeah, I did that.
So yeah. So if you know about sort by, more power to you. But my expectation was that you'd use sort with, and you do this.
Oh yeah. Oh yeah, we can totally do.
All right. So now find the longest string using reduce. That one, I guess it's more difficult. Because the reduce thing needs to, the reduction operator does what? It takes 2 strings and it gives you back the longer one. So I guess I could try to write it inline. So, and I'd have to say if x.length is less than y.length, then it gives me y and else x. I guess that does. So I can put it in here. This is probably the outer limit of something that you would want to do with an anonymous function, right? It's getting to be pretty long. So I saw that a whole bunch of you defined this as a separate function, and that's certainly fine. And then, we'll have to give it some snapper name, say longer. And with a def, I guess then this turns into an equal. And at that point, then you can just pass the function in here. Oh, and I have to now give the parameter types, right? Because it can't infer them.
Oh, yeah.
So I expected that most people would probably do that, but either way is, of course, just fine. All right, now to the more complicated things. So the currying. So we write a function make min. So it's def make min. What does it take? What kind of function? Thanks. So, and I'll call it C string to Boolean. Okay, and what does it produce? It produces a function string to string, okay? So I now have to yield a string. Okay, which string do I need to yield? Well, if x compared to y is in order, then I give x and otherwise y. So, and how do I find out which comes first? Well, I use my comparator. Okay, let's put this here on 2 lines. So here it is. Let's try it out. We'll call make min. We'll give it some comparator. Do I have a comparator here somewhere? Well, let's reverse the comparison. And now I need to give it 2 strings. And then it returns the smaller of the 2, but because I inverted the comparison, then it's the larger of the 2. Okay. So now I said rewrite this here using the curry syntax. So in the curry syntax, what do? I take out the equal, I smush these 2 parentheses together, and I turn this arrow into an equal. Same thing.
Wait, so I thought currying there was indefinite is like you consume like one argument during
Yeah, and so I guess I didn't really write it. I need to rephrase that question. So this is what I meant you to do. So I guess where people were confused is they wrote this thing so that C, X, and Y are all parameters. And that would be the uncurried version. So I realized that they make min the way I was curried, right? It eats something, then it produces a function. And so all I wanted you to is to compare these 2 syntaxes. I didn't mean to rewrite it the other way. I mean, it's instructive to do that too, but that's what I was after.
So both of them are currying.
Yeah, so they're both curried. Yes, they're both curried. I understand it. I didn't phrase that question very well. So what I was after is to compare these 2 ways of writing that curried function. Whether you use the 2 parentheses or whether you use where it explicitly produces the function. And so the style with the 2 parentheses, it looks kind of clean. You just have to realize what goes on behind the scenes. So I have no preference which of those styles you use. When I did homework 3, I normally actually use the explicit style because that's what I'm used to from other languages. But I found it kind of liberating to use this style with the 2 sets of parentheses. It made a lot of sense. So try it both ways, and you can do half of the homework one way and half the other way, and then come to a judgment as to what you personally prefer. So now we need to make this thing generic. So generic means that we don't just want it to use for strings, but for any type. So all I have to do is replace all the strings with T. And then I put an angle bracket T here. Now, of course, when I do that, unfortunately, this line no longer works here because it can't infer right now what the greater than is. We could fix that, but I want to move on to something else. So in step 3, I had this generic max function that, given a comparator, computes the largest element in a list. Notice that there's a flip of the x and y in here. So when I'm reducing, and I have to call my comparator, which always gives me the lesser one. But if it says that x is less than y, then I produce y. So this thing gives me the larger of the two inputs. And so I keep taking the larger as I walk down the list, and that gives me the largest element in the list ultimately. So we can just try this out. And so if I do max of, what's this, LST, and now I'll give it some comparator of strings by, let's say, x dot length is y dot length. Then I get the longest string out of this. But if you do what you would like to do and use the nifty underscores, so let's try that, max LST, comma, underscore dot length less than underscore dot length, then that will not work because the type inferencer doesn't know what types the underscores are. And the reason for that is that the type inferencer tries to solve all of these constraints at once. And the way it's built, it just can't do it. And here you can solve this type inferencing issue by rewriting max to be curried. So I'm going to take this comma out and put in parentheses. And that's the only change I'm making. Now, of course, I also in the call have to make the change. So instead of the comma, I have the closing and the opening parenthesis. And now the abbreviated call also works, because now the type inferencer looks at max, says, oh, it's this generic thing here. It looks at LST and says that's a list of int, and at this closing parenthesis, it is willing to resolve that t must be int. Then it can use that information to figure out what the types of the underscores are. No, sorry, t is string, right? LST is a list of string. So then this is a string, and it can take the length. And so that's nice, because it enables us to use the underscore trick with the function that max takes. Max was built to take a comparator function, and we want that function to be specified as easy as possible. Yes?
So if you specify the function without the curry syntax, you can just say like val select greater or select less would be just like make min surround like is a greater than or is a greater than less than b. But if you use the curry syntax, if you want to get that lambda for selecting either one, you have to put an additional set of parentheses afterward and then put underscores in for the arguments.
Well, it's not that I have to, but I'm able to. It's a human urge to want to use the underscores, right? Less typing.
Oh, no, I mean, maybe I'll ask you after this, because it's giving me an error if I try to use the curry function to get a lambda that I can use later on.
Okay, I'd have to look at your thing.
Okay.
Yeah. So with any of these mysteries, yeah, feel free to post them all on Piazza. And any such thing, that they're always interesting to look at. So the point I want to make is that we like the syntax with the underscores. The syntax with the underscores only works if the type inferencer can infer the types of the underscores, and by putting in this extra set of parentheses, we allow it to use the first set of parentheses to infer the types, and then we can use them in the second one. That is such a useful and attractive thing that several functions in the standard library that we will be using often use the same trick. So we'll be using a function called fold, for example, that does the exact same thing, and it orders the arguments in a slightly illogical form so that it can use the first set of arguments for type inference so that the second one, where the function parameter comes in, can then benefit from that result. So if you see some of these functions in the standard library documentation, which we will start to learn on next Monday how to use, you will often see this. And then the answer is they don't do that for any other reason except to help out with the type inference and to give us more chances to use the concise function notation. So that was the other reason I wanted to cover currying, because you will need to know it next Monday. All right, that's what gets us to the end. Homework is due next Monday night. By now, everyone knows it's best to start it early. If you do it now, and I've seen some people already did start and submitted something. So go ahead, do a few. This you can perfectly well do 1 or 2 a day, and it'll feel like no work at all. So go for that. Any questions? Put them on Piazza. Don't be afraid to put code on Piazza as long as the code doesn't work. All right.